In this lesson, we build a crisp mathematical and visual understanding of transformer self-attention and connect it to a continuous optimization viewpoint that explains why softmax appears naturally. We will proceed step by step and keep the screen clean and readable at each step. We start with the inputs. Suppose we have n tokens, each mapped to a d-dimensional embedding. We stack them into a matrix big X in real n by d. From X, we form queries, keys, and values by multiplying by learnable weight matrices. Big Q equals X times WQ, big K equals X times WK, big V equals X times WV. Scores are computed by S equals QK transpose divided by square root of D sub K. We turn each row of S into a probability distribution using row-wise softmax to obtain A. Finally, the output is Y equals AV. To make this concrete, consider 3 tokens. Pretend the score matrix S is chosen for easy numbers as follows. Row-wise softmax normalizes each row to positive numbers that sum to 1. Interpret each row of A as how much one token attends to every token, including itself. Why softmax? A powerful view is that each attention row solves a small continuous optimization problem. For a fixed query row with scores vector S, the attention probabilities P are the solution of maximize over P in the probability simplex, P transpose S minus tau times the entropy of P. This is a strictly concave objective, so it has a unique maximizer. If we write the Lagrangian and set derivatives to 0, we get the well-known closed form. Pj is proportional to the exponential of Sj over tau. After normalization, P equals softmax of S divided by tau. In transformers, we use 1 over square root of D sub K as a scale, which corresponds to a temperature tau equal to square root of D sub K. The same solution can be viewed as a kernel normalization. Define Kij as the exponential of Sij over tau. Then each attention row is just that kernel row normalized to sum to 1. A equals D inverse times K, where Dii equals the sum over J of Kij. This makes attention a smooth data-dependent averaging of the value vectors. Since models are trained end-to-end, it helps to recall the Jacobian of softmax. For one row with probabilities P, the derivative of Pi with respect to Sj equals P, I times the Kronecker delta Ij minus P, Ipj. The scale 1 over square root of D sub K keeps score magnitudes moderate, which stabilizes both the forward distribution and its gradients. Real transformers use multiple heads. Each head repeats the same math with its own WQ, WK, and WV, then concatenates the head outputs and mixes them linearly. This is just parallel copies of the same optimization-driven attention. Let us finish the example by applying A to simple values V. Pick 3 two-dimensional values to keep arithmetic small. Then Y equals AV does a weighted average of rows of V for each token using its attention weights. Summary. Inputs to queries, keys, values. Scores equal QK transpose over square root of D sub K. Attention equals row-wise softmax of the scores. Output equals attention times values. Softmax appears as the optimizer of a linear objective plus entropy over the simplex, or equivalently as row normalization of an exponential kernel. That is the mathematical and optimization backbone of self-attention.